For this Wednesday lab, we're going to look at the hardware that implements these binary arithmetics. And again, everything is provided on that chapter 7 PDF that I have on Canvas. And we're going to start with understanding the 1-bit header, half header, and then full header, and then understand these ripple carry headers. We know that in a computer, the addition of binary numbers is performed by this hardware called Arithmetic Logic Unit, or ALU, that receives a set of bits as input and produces the result. And it also has the ability for us to indicate if we want to subtract or sum the values that you have at the input of the hardware. The motivation behind this hardware is, firstly, we want to implement this simple binary addition. So the ones that we learn this Monday, we have 0 plus 0 gives you a 0, 1 plus 0 gives you a 1, and 1, 0 gives you 1. And also a hardware that allows you to include the carry in that is coming from a previous column. So let's see the hardware that handles first just this part over here. And in order to do that, we need to go and cover a little bit of logic gates. If you took Intro to Mechatronics Systems 1, you probably are in good shape. You're familiar already with gates. If you did not, do not worry, don't get overwhelmed. Next week we'll go over all these gates. For now, we are just going to focus on two gates, the AND gate and the exclusive OR gate. The Boolean expressions for this will be A and B, and over here we have A, exclusive OR, B. Once again, don't get overwhelmed if you never saw this. Next week we'll go over all these logic gates again. Right now, we just need these gates to implement our binary additions. This exclusive OR is going to do the summation, and the AND gate is going to take care of the carries. Here you have an example, a drawing, a block diagram. We call half header because we're just dealing with simple additions here. The 0, 0, 0, 1, 1, 0, and that's it, only these three. And at the most also the 1, 1, 0. Also we take care of that one. What we don't care is the carry that is coming from a previous column is not taking into consideration on an half header. And notice here that we start abstracting, and we have a block diagram, and we give the input bit 0 of y and bit 0 of x, and then we have bit 0 as our summation, and then the carry. And if I zoom in inside of this half header, I have the logic gates that are responsible to do that addition and that carry. Let's see the full header. So the full header, the only thing differently, if we look at the block diagram, is now includes the carry in that comes from a previous column. That's why it's called the full header. It's going to do the full addition that we learned last Monday. What's the hardware for this? Well, it's no different than the half header, but this time you have an exclusive OR with 3 inputs instead of 2 inputs, and then you have 3 AND gates connected with your OR gate over here to give your carry out. Again, don't get overwhelmed. For this lab, you just need to follow block diagrams and represent what it's here. Next week, we'll go and cover logic gates more in depth. So we cover full headers and half headers, and they are just taking into consideration 1 bit at a time. And what if I want to apply a summation like this? I have 2, 4, 6 bits, and I want to perform this addition of 6 bits. What do I do? Well, this is what it's called a ripple carry header. And what you do is you start constructing the ripple carrier with half headers and full headers. So let's see how do we do this. Let's see an example with 3 bits. I have 3 bits for my number y here and 3 bits for my number x over here. My summation is going to be, or my result is going to have 3 bits. And the first thing that I'm going to do is I'm going to connect an half header between my y0 and my x0. so I can get the result of my Z0. The carry out, if there is any carry out, is going now to propagate and connect to the next module that I'm going to connect a full adder, because the full adder takes into account carry ins. But notice now that the inputs of this full adder are bit number 1 and bit number 1 of the respective number. And then at last, we do our third bit, the last bit. The carry out of this full adder feeds to the carry in of your last module, and the third bit, Y2 and X2, are the inputs of your full adder that gives you your third bit for your answer. This is what it's inside. If we start zooming in inside of those modules, we have those exclusive OR gates and AND gates. And we can also use ripple carry adders just with full adders. If we go to our first module over here, and if we substitute the half adder with a full adder, but the carry in we put a 0, then we are using the same hardware to implement an n-bit carry adder. So here you go, an n-bit ripple carry adder. It's just adding a bunch of full adders together, and you can build pretty much any size of arithmetic logic unit just by building these modules together. So what's going to be the goal of this lab on Wednesday? I'm going to ask you guys to watch the LabVIEW videos first, the sub-VIs, arrays, for loops, case structures, so all these videos over here first. And then I'm going to build an half adder and a full adder. And I want to see if you guys can give it a try and try to implement something like, as we have here, a 3-bit ripple carry adder.